In this video, we're going to be looking at compounding and how that affects interest rates. And so obviously we are going to start off with our basic lump sum, present value, future value formula. And again, we can write that, a couple different ways. So let's get these in here. And these are what we call simple lump sum formulas because there's only one present value and one future value in this formula. And so the only difference between these two values comes from the effect of interest. And so so far we've only mostly looked at what happens in a one period setting where you put money in up front and then you wait for a time period and then you get your money back at the end, and it's a larger value because of the growth from interest. So what we're going to look at now is what happens whenever we get multiple periods in a row. And so in a multi-period setting, it could be something like, okay, well, how much is the future value in 3 years if I invest $100 today and the return that I can expect is 5%. Well, T is 3 in this situation, and so this means that we're going to put $100 in, and we can make a little timeline of this problem. And what it looks like is this. Today we give up $100. A year goes past. We don't do anything. We just leave the money. 2 years go past. We don't do anything. We just leave the money. And then at the end of the third year, because we're going 1 year, 2 years, 3 years, right, out like this. At the end of that third year, how much money is going to be in that account? Okay, so the way we would do this is, if we want to do it piece by piece, you can say, okay, well, if we go forward 1 year, all right, then the future value at time 1, well, future value in 1 year would be 100 times 1 plus the rate of return raised to 1 year. Okay, well, that's going to be, it would be worth $105, and that comes from, we get 100 times 1, we get our original investment back, and then we get 100 times the 0.05, we get another $5 back, and this is interest, and this is the principal, okay? Realize that it's not the clearest writing, but there you go. Principal and interest, right? That's what we get back. And so that means that our total value in 1 year would be $105. Now, if we leave that and we don't withdraw it from the account, it would roll forward and we would have a future value in time 2. Now, in year 2, we are going to gain interest not only on the principal, but also the extra interest that is in the account. And so the future value in time 2 is equal to the future value in time 1 times 1 plus the rate of return to the first power, because again, the distance between this value and this value is 1 year. Okay, so that's where these little subscripts become handy, because you can easily see, well, the difference between year 2 and year 1 is 1 year, so that is how many years of interest I'm going to be earning. So we can put that into the math, drop in the actual value, right, 105. 1 plus r is 1.05. Raise it to the first power. All right, now, what's going to happen? Well, we're going to get 105 times 1, plus we're going to get 105 times 0.05. Okay, now that ends up being 5.25. Okay, so the total here is $110.25. Okay, and if you want to break it down into some even more pieces, right, this would be the principal from year 1, and this is the interest during the second year. But the principal from year 1 is composed of the principal at time 0 and interest from year 1. Okay, so ultimately in this account, there's our original $100 investment, there's $5 in interest on that $100 from the first year. In the second year, we got another $5 of interest on the original 100, okay, and I know that may be starting to get kind of complicated to see, but, you know, if you think of this 105 here as composed of 100 plus $5, you could kind of say, you know, this is 100 plus 5 times 1.05. Well, you're going to get your $100 back. You're getting the $5 back from interest in the first year. The $100 sits through the second year, gets another 5% interest, and then we get 5% interest on that $5, which is another 25 cents, right? And so this is our total. We're getting the original principal. This is our interest from time period 1 on the principal. This is the interest in time period 2 on the principal, and then this is the interest on the interest in year 2. Okay, and so we're starting to see what's going on here. You're getting more interest in each year because in year 1 you gained $5. In year 2 you gained $5.25, and the difference is the extra 25 cents came not because of your principal, but because of the interest that was left in the account. And so this is interest on interest, and that is compounding, right? Compounded interest, where not only your principal is gaining interest, but your interest is gaining interest. So if we go forward one more year, all right, so in year 2 we had 110.25. All right, well, this is how we get to that future value 3. All right, so we are going to say that future value 3 is equal to the future value in year 2 times 1 plus r to the first power, because again, there's 1 year difference in these values. Well, that is equivalent to 110.25 times 1.05 first power. Okay, so what's going to happen? Well, we're still going to get to keep our original $100. We had $5 from year 1's interest. We get $5 from year 2's interest, okay? And then we get the 25 cents that came from year 2. All right, now this is just future value 2. So what's going to be the additional money that we get for that third year? Well, we're going to get 5% times the $100, so we're going to get another $5. We're going to get 5% times this $5. Well, that is another 25 cents. You're going to get 5% of that $5, which is another 25 cents. And lastly, you're going to get 5% on this 25 cents. So this came in year 3. This came in year 3, this came in year 3, and the last piece is we get interest on the interest from year 2. Okay, so we get 5% on that, which is 0.0125, and that came from year 3. And if we add all this together, and I ran out of room, so let's say future value in year 3 ends up being 100, 5, 10, 15. Okay, so 115. Okay, then we're going to get 25, 50, 75, 76, 25. So 1.7625. And this is how much money we would have at the end of the third year. Okay, and again, that represents our original principal. We got 3 years of interest on that principal, $5, $5, $5. Now, on the $5 from year 1, we got 2 years of interest. Well, there's 25 cents, there's 25 cents. On the second $5, we got 25 cents in year 3, and then the 25 cents that came from year 2, that got a year's worth of interest. And so we keep piling this up, and if we keep going, this thing just gets more and more complicated. And I know you only went 3 years because at this point we're starting to get a lot of little pieces going on, and this represents why compounding interest is so powerful, because over time, what ends up being the value of the account starts to become quite large in terms of how much of the money in the account was You originally put in $100. How much of the money in the account is accumulated interest? Over time, the proportions shift where there is more interest in the account than there was principal, right? And that's a good thing if you're saving. If you're borrowing money, that's a bad thing, right? Whenever you borrow money, compounded interest can really start to hurt you, okay? Because over time, if you don't pay that balance off, it keeps growing, and every time period that passes, it's growing faster and faster, right? So if you're saving money, your savings are growing faster and faster over time. If you're borrowing money, your debt is growing faster and faster over time. And so this is the basic compounding that goes on in simple time period interest rates. Now, next we have to look at the way we actually handle compounding is often not once per time period. Sometimes we do compounding that occurs quicker than our standard measure of time, which is, we usually say a year, right? Well, it's very common for compounding to happen multiple times a year, and so we're going to look at, well, what happens in that case. So let's clear the board and then we'll tackle that. All right, so we are now going to tackle multiple compounding periods per year. All right, now, there are a couple different ways to look at this. In some respects, this is no more complicated than this formula, but the way it's written can look a little more complicated, so I'm going to try to very carefully talk about how compounding works and how periods work. And what do we mean when we say, you know, an annual percentage return, APR, how that translates into the actual effective interest rate over a year. You know, typically the loans that we deal with as consumers are car loans, home loans, you know, student loans, credit cards, and almost all of those, whenever it comes to payments, the payments happen monthly, okay? And that means that the account is updated monthly, and so it's very common to see 12 compounding periods per year. Okay, and this formula, if we assume that T measures a time span in years, this doesn't work to actually tell us the effective interest on those years. So we're going to have to look at that. Now, the first thing I'm going to point out is these are just letters, and we have defined what these letters mean. And so in some sense, this letter T doesn't have to mean 1 year. It literally just stands for a number of time periods, and then we impute meaning to, well, how long's the time period? And so we can say it's 1 year, but it could just as easily be a month. It could be a day. It could be a standard whatever length of time we want in the problem that we're working. So here's one way to look at compounding interest rates. It's not just dealing with interest over a year, it's interest per period. Okay, so one thing to do is to first define, whenever you say an APR, this is an annual percentage rate. This is also what's typically called a nominal rate, meaning this is how we talk about rates. This is the name that we give interest rates when we talk about them. So whenever you go borrow money on a loan, they will tell you the APR on that loan. All right, that means this rate will typically stand for the interest rate per year. It's an annual percentage rate. That does not mean that this represents the interest compared to principal that you would pay in a year, which I know is very confusing. And the problem is this, this doesn't account for compounding. It's just a nominal rate that is used to figure out the impact of interest. Okay, so the way this gets used, we will change this formula slightly, okay, so that we're going to do this. The future value at time t means after this many years. But we're going to have to work in the fact that interest gets compounded more often than one tick of time in our model. So it's still based on the same math, but now we're going to do a little modification. We're going to take the r and we are going to divide it by what we're going to call m, and then we're going to raise this to t times m. All right, now this m is compounding periods per t. Okay, so if t is in years, m stands for the number of periods, the number of subdivisions for compounding per year. Okay, and again, it doesn't have to mean that. That's just how we usually define the length of time that t represents. Okay, t for us mostly going to mean 1 year. Okay, so m is the number of periods per year. That means that this r is being divided into m number of pieces, and so r is APR. So they are telling you this number when they tell you the APR. Now, here's the thing. If you borrow this amount of money today and pay off your loan all in one lump sum at the end of the year, this rate won't tell you how much more money you owe, which means it's not really the true rate of interest on an annual basis. What's going on in this formula is we are taking this APR and then we are breaking it into a number of chunks. And so another way to think of r divided by m is equal to what we would often call a periodic rate, periodic interest rate. Okay, it is the actual rate of return per true period in this problem, because there are actually, let's do a little example here. Let's say that there is monthly compounding. We're only going to leave the money for 1 year. Okay, if there is monthly compounding, so okay, well that is defined as m equals 12, t equals 1 year. All right, which means that number would be 12, and we would break the APR into 12 pieces, and each month would earn 1/12 of the stated APR. Now likewise, however many years are in that problem, there would be actually 12 times that many time periods to calculate compounding for. Okay, so that's the impact that this formulation would have. So, one thing to note is you could also say that this t times m equals the total number of periods. Okay, not the number of years, the total number of compounding periods, because t is just a number of years, and if we've got multi-period compounding within each year, then t does not accurately reflect the number of compounding periods. T times m tells us the total number of periods. And so a different way to think about what this is, it's just a way to calculate the real periodic r and to calculate the real number of time periods. Okay, because again, remember, this t, kind of arbitrary as far as how long does t stand for, right? What time period does t stand for? So it is actually this same formula, it's just that in this version, the way we've written it, t doesn't stand for years, it stands for total number of periods. And r does not mean APR, it means periodic r. Otherwise, the number here is going to be the exact same. I mean, it's only going to be one number, right? If your interest rate is 12% APR and your compounding period is 12, that is equivalent to 1% per month, and then t times m would tell you the total number of months. Okay, so you could easily think of it in this format, except for t would be months, r would be percent per month. But since we typically use years, then this is how we often have to do the math, because they give us an interest rate that is not per month. They give it per year. And then we have to break it into, well, what does that mean per month? And then we have to take the number of years on the loan, multiply it by the number of periods per year, which again, if it's months, then that's 12. And this is how we would handle calculating the effects of compounded interest whenever you've got multiple periods per year. You'd use this setup to tell you, what the true periodic rate of return is and what the true number of periods are. Okay, so I've cleared this up to give us some more space, and we're going to do a very simple example. All right, so what we're going to do in this simple example is we are going to say that we are going to borrow $100. We are going to pay off that loan in 1 year, and the terms are 10% rate of return, 2 periods per year. Okay, so interest is compounded once for every 6 months. Okay, so now we're going to start writing down and documenting our stuff, right? So we're going to say that the initial value of the loan is $100. Okay, R is the APR, that is their nominal interest rate that they tell us, which is going to be 10%. M is the number of periods per year. Well, if you're calculating interest once every 6 months, there are 2 M's, 2 periods per year. T, we're going to make this simple. We are going to leave that for 1, and that is, again, years. All right, well, then we plug in to our formula these numbers. 100, okay, R divided by M. Well, that is going to be 5%. So 1.05. And then T times M is 2. All right, now, if you notice, this is what I was saying. This formula ends up being equivalent to, well, what if R was 5% and T was 2? Right? Because periodically, there's 5% interest and there are 2 periods. So it is the same formula. It's just a way to do it whenever T is defined in years and you've got multiple periods of compounding per year. Now, we've done this before, right? We did this in the earlier problem, right? This is equivalent to that earlier problem, except for now we've just defined the time periods to be a different length. Okay, well, what are you going to get? You're going to get $100 back. You're going to get, well, there's going to be a $5 return for the lender in the first 6 months, and then in the second 6 months, there's 5% interest on the 100, there's 5% interest on the 5, which is 25 cents. You add all this up, it's $110.25, and that is how much you would owe after 2 years. Now, here's the thing. This is different than just paying 10% per year, right? 10% per year would look like this, okay? So if I do this, the exact same problem, except for now, it's 10%, but there's only 1 period per year. Then the future value, and I even messed this up, right? I use that exponent, and the future value after 1 year would be 110. So the future value 1, PV 0, 1 plus R divided by M to the TM ends up being 100 times 1.1 to the 1, and that equals 110 with no pennies. All right, these are not the same. This is the impact of compounding. Because there was an extra time period, you actually owe more money if you've got 10% APR compounded twice a year versus 10% APR compounded just once, right? There's an extra quarter in there. Where did that come from? Well, that's because, if we draw a line here, this is the value that would have been assessed at the end of the first 6 months, right? This is equivalent to $100 at the beginning, right? That's your return of principal, and a one-time $10 payment. Well, here they give you half of this $10, right? They give you $5 early. That you get some of the value in the account earlier than this value. So that $5 hits in 6 months. It accrues to your balance. If you go to pay this thing off early and you're trying to pay it off 7 months in, you're going to owe $105. Now, in the next 6 months, you get another 5%, but then this is the difference. That $5 also gets a 5% return. You have to pay back more money now because of compounded interest, all right? Whereas this, there was no extra compounding, all right? It only happened in 1 year. All right, so this is the example of compounded interest and how it will be different, right? Whenever you increase the compounding periods, it will change the impact of the APR, right? All right. In these two loans, the APR is exactly the same. The difference is the rate of compounding. If you go and you borrow these loans, they will say, hey, this is 10% APR, this is also 10% APR, but after a year you would owe different amounts of money because of different compounding periods. Okay. In general, the effect of compounding increases with the number of compounding periods. Right? So as you increase M, the overall impact changes. Right? It goes up with M. The next thing we want to look at is, well, if the effect of M increases as M increases, how big can we make M to make this future value larger and larger? Like, if I just increase the rate of compounding, holding the rate of return constant and keeping the total holding length, right, the total time length constant, and all I'm doing is I'm just updating the rate of interest more and more and more, right? Updating my compounding more and more and more. Is there a limit to that? And the answer is yes, there's a limit to that, okay? And it ends up looking like this, okay? The future value is going to be E raised to the RT power, okay? And so E is an actual, that's a number, it's like 2.7 blah, 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 right? It's like this, right? So this is an actual number, meaning if you make M equal to infinity, right? This is also called continuous compounding. All right. Compounding happens every moment, right? Every atomic cycle we are compounding interest. There actually is a limit to the effect of compounding, and it's represented by this, right? So here's the weird thing. These two formulas give you the exact same answer if you make M infinitely large. All right, so which means this actually is this formula. Okay, that's crazy because it looks totally different, but it is this formula if M equals infinity. So I can say if, then this is the way to do this math, right? If M is any number other than infinity, by definition being less than infinity, then you use this version. But as M gets really, really big, this gets pretty close. Okay, so that's why we call it a limit. As M gets really large, it starts looking like you're doing this math even if you're technically not. Now, in the real world, typically the most frequent compounding that you're going to have to do a discrete calculation, like how big can M be before we just switch to using this formula? Daily. That's kind of the most frequent compounding that you would actually do this formula instead of this formula. And daily would be M equals, 365-ish, depending on if it's a leap year and blah, blah, right? I mean, that's pretty much it. Once M gets larger than that, and the reality is it usually doesn't get bigger than that. It's either, hey, we go from annual compounding, then you get semi-annual compounding, which is twice a year. Maybe you get to quarterly compounding 4 times a year. Then you go to monthly compounding 12 times a year. Then maybe weekly, so roughly 52 times a year. Then you're going daily, right? 365. The next iteration is continual compounding. And so you do see this in derivatives sometimes. Futures, forwards, option valuation, that's the kind of place where continuous compounding exists. Outside of that, you won't see it quite as often. Credit cards will often do monthly or daily compounding. You will occasionally, if you're careful, you'll note that your credit card might be doing daily compounding. Now, as the credit card company, why would they want to do that? Well, the higher the compounding, the larger the impact of the interest rate, which means, hey, they're going to tell you, let's say that their APR is 14.99%. Well, the actual impact of that 14.99%, remember, increases as M increases. So if they have M equal to 1, then this is the actual interest that you would pay after a year, right? If you borrow $100, you'd owe, about $15 in interest at the end of that year if M equals 1. But the bigger M gets, the more money you will actually owe them. And so if they're using daily compounding, that's a way to be able to tell you, hey, your APR is 14.99%, but actually be able to get more money if, you leave a balance and owe them interest. And so that's where you got to be careful whenever you're borrowing money or investing for that matter. What's the compounding interval? Because the stated interest rate may actually come out to be different from the actual rates that end up applying to your money because of increased compounding.